Well, welcome to this Conservation Applied Research and Development webinar. I'm Mary Sue Lobenstein, the R&D Program Administrator at the Minnesota Department of Commerce, Division of Energy Resources. Next slide, please. With me today is Mark Garofano, who is the Energy Engineer at the Division of Energy Resources, where he performs engineering reviews of custom efficiency projects and leads the department's efforts to maintain and update the technical reference manual that utilities use to calculate the savings and cost effectiveness of their conservation improvement programs. Mark is also the project manager on the research that is the subject of this webinar. Our presenter today is Ben Schoenbauer, who is a senior research engineer for the Center for Energy and Environment. Ben conducts research on new and innovative technologies and ideas dealing with residential and commercial energy efficiency. His work includes identifying new opportunities, conducting field research, identifying and pursuing funding opportunities, and disseminating the results of research he's conducted. Ben's areas of focus include water heating performance, surface water heating, residential HVAC systems, and beneficial electrification. Before we start, I'd like to go over a few webinar basics. All attendees will be in listen-only mode. As questions occur to you during the presentation, type them into the question box in the GoToWebinar panel and send them to us. We will address all questions at the end of the presentation, but if for some reason we don't get to all questions, we will answer them later and email all participants a copy of the Q&A from the webinar. This webinar is being recorded and will be available on both CEE's and the department's websites at a later date. Finally, the slide deck for this webinar is available as a handout on your GoToWebinar panel, and you can download it at any time during the presentation. This webinar is one in an ongoing series designed to summarize results from research projects funded by Minnesota's Applied Research and Development Fund. The Applied Research and Development Fund was established in the Next Generation Energy Act of 2007. Its purpose is to help Minnesota utilities achieve their 1.5% energy savings goal by identifying new technologies and strategies, improving the effectiveness of utility conservation programs, and documenting CO2 reductions from conservation programs. A utility may reach its annual energy savings goal either directly through its conservation improvement program or indirectly through energy codes, appliance standards, behavior, and other transformation programs. About $2.6 million of this fund is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Since the legislation was enacted, the CARD program has had 8 funding cycles with 22 RFPs posted, received nearly 380 proposals, and funded 92 research projects, representing over $21 million in research dollars. And as you can see by the pie chart here, projects funded to date have been in all building sectors. The subject of today's webinar is the residential sector, and reports on a project which assessed the efficiency, savings potential, cost effectiveness, and comfort of new heat pump technologies designed for operation in cold climates. So I'm going to turn it over to Ben now, who's going to tell us about the results of his great research project.
Hi everyone, thanks for attending today. So I'm going to talk a little bit about the results from our field assessment of cold climate air source heat pumps. As alluded to, the final report will be out for this project shortly and available on both the DR and CE websites, so if you're looking for more follow-up information, that will be available. So a little bit of background for anyone that isn't familiar with the Center for Energy and Environment. If you're not and more interested, probably the best place to go is to our website, mnce.org. But a little bit of background, we kind of do all things energy and energy efficiency. We run programs, including the Home Energy Squad and kind of one-stop commercial lighting programs. We do planning and consulting. We have a loans group that does financing. We do a lot of policy work as well. And then the group that I'm a part of is the research group, and we do research into lots of different areas. We've done a number of card projects over the last handful of years, and we'll dive deeper into one of those on cold climate air source heat pumps today. So this is just kind of a little overview of what we're going to talk about today. Start with a little bit of the background on the technology and the recent advancements that have been made. Go into the opportunity of why we were interested in this technology and why it was a good technology to study as part of the CARD program, and then start to get into some of the results, looking at the kind of things that are important for the installation and operation of the system, as well as, and then into the results of the performance, and get into some conclusions as well. So for people that aren't familiar, here's just a little background on how these systems work. So an air source heat pump is a space conditioning device that does both heating and cooling in residential homes. At least we're focusing on residential homes for this project, and it uses forced air to do that. So it works a lot like your typical cooling system or your typical air conditioner. In the summer, it does provide cooling. It simply transfers heat from inside the house through a refrigerant system to the exterior. What differentiates air source heat pumps from traditional AC systems is that system can then be run in reverse to provide heating in the winter. And so that's what the top side of this figure illustrates here, is that you're moving warm air from, or you're moving heat from the outdoor air into the house. And this is capable even at very cold temperatures. And that's really the advancement in technology that's been made in the last couple of years, is generating heat at cooler and cooler outside temperatures. So some of the systems that we'll talk about today are capable of moving heat from negative 13 degree air outside and heating your house, even at those cold temperatures. And actually, since this project has been underway in the last couple of months, there's been some even further advancements to the technology that's moved that number well below negative 13 down to the negative 20 degree range. So these systems have really made significant steps forward that really open up the potential to deliver energy savings in cold climates and heating dominated climates. And so that was really the technology behind this project and reason we started to look here. One thing I will point out at this point is that we really focused on the heating performance of these systems for this project. That's where the innovation occurred here recently. But one thing to keep in mind is that there are cooling savings typically associated with these systems. Because the technology is so advanced on the heating side, that comes with an increased level of performance on the cooling side as well. And so while I won't focus on it, I will mention a few times throughout the webinar the impact on the cooling side and kind of the savings potential that's available there. But again, we didn't focus on that. So most of you are probably familiar, at least those of you from Minnesota are familiar, that the severe shortages in propane we had a few winters ago, and some of the problems that caused for some homeowners in the state. There's a large chunk of our state, maybe 30–40%, that is still using delivered fuel as their primary heating source. And then there's another significant group of people that are using electricity or some other source because natural gas isn't available. And so we wanted to try to look at some opportunities for these people to get off their inefficient delivered fuel systems, and heat pumps provide a pretty interesting option. And so that's really the focus here, is to look at houses that don't have traditional energy efficient gas heating technologies available to them, and focus on looking at solutions to help ease some of those burdens. Obviously, we don't expect to regularly go back to those extreme conditions where there were delivered fuel shortages, but even in under good conditions, there still is some pretty seasonal impacts to the cost of delivered fuels in the state. So a little background, or a little overview of the field study that we conducted. So we really wanted to focus on, now that these technologies are out, they're new, they have claimed performance, but how do they actually work when you actually put them in a real cold climate? Some of these systems have been installed and demonstrated in more moderate climates on the coasts, but they haven't really been tested in a climate as cold as it is in Minnesota, and especially in the northern part of the state. And so we really wanted to look at houses that were representative of those homes that didn't have gas available. And so you can see from this map where our installs were for this project. So we had 6 sites total that we installed. We had both ducted and ductless systems. I'll get into that description if you're not familiar and the differences as we move through the presentation. But we had some in the metro area, one down a little bit further south in the state, and then sort of one in the western side, and then a couple in the northern part of the state, to really try to get a representative performance of the different climates in the state and in cold climates nationally as well. And we really wanted to look at how do these systems really work when you put them in real homes that have real loads, and sort of make some summaries and results and conclusions on how to incorporate those best into SIP programs moving forward. I won't go too much into depth here, but this is just an overview of the instrumentation that we installed with these systems to give you an idea of how detailed the data was that we were collecting. So this is a kind of a sketch of a heat pump running in heating mode. So you can see here how it's pulling air in from the outside, transferring that heat into the refrigerant, bringing that into the house, and then using the coil, much like an A coil for an air conditioner, and a fan from a furnace to transfer that heat into the home and heat the house. And you can see that we're measuring power consumption of various components throughout the system, as well as the delivered energy to the house, both in terms of airflow and the temperatures of that air. And so this really lets us characterize this system on a very detailed basis. And so as we started to collect data and install these systems, we found some very important areas of that install that really help you set you up for success as you move into operation. And these are important areas to know if you were to be developing a program, or things to think about to ensure that you get good success in your system operation. So I mentioned before that we looked at both ducted and ductless systems, and so here we'll start to talk about the differences. A ducted whole house air source heat pump system looks very much like a traditional AC system. It's got an outdoor unit and a line set that comes into the house. You see the outdoor unit on the left there. The line set's coming in at the upper right-hand corner of that picture on the right, feeds into the ductwork just above your furnace, where your coil is located, and then your kind of standard furnace below that. And that furnace also acts not only as the fan to move the heat from the heat pump, but also as your backup heat. And so this is sort of the ducted whole house system that feeds right into your likely existing forced air distribution network, ductwork, and can heat the whole house, anything that's hooked up to that system. A ductless system is named such because it doesn't have ductwork, so it's very much the same type of system, but it has an outdoor unit and a line set coming into the house, but instead of connecting up to your central duct system, it has an indoor unit, or typically called a head, that is placed in the home and transfers heat directly out of that unit. And so because it doesn't have a distribution system, it's really limited in effectiveness to the area surrounding that system, and we'll get into a bit about the limitations and benefits of that approach. So here's just an overview of the equipment that we installed. You can see there's 4 ducted systems in green there, and the 2 ductless systems down at the bottom. I'm not really going to get too much into the differences of these different types of systems. There are some small differences in performance and operation, but for the most part, the systems operated in a similar extent. Another interesting thing here to point out is the size of these systems. So because the ducted systems are designed to meet the whole load of the house, or to at least supply heat to the whole house at different points in time, they're much larger than the ductless systems. So you kind of have 3-4 tons. You can get them up to 5 or 6 tons, down to 1.5 or 2 tons, but typically they're in the 2 to 4 ton range. On the ductless systems, they're much smaller. They typically come in 1.5, 2 ton units. So just because of how they're designed in their applications, that there's some different sizes. So as I mentioned previously, The big advances in the technology here is this cold climate performance, and so this is just some manufacturer rated data. This is right off the manufacturer specifications for one piece of equipment. This is just one of the pieces of equipment that we actually installed, but these are the laboratory test conditions as rated by the manufacturer. And so you can see here, we're looking at both the capacity or the amount of BTUs delivered to the home from the system in the blue, as well as the coefficient of performance, which is a measurement of the energy delivered to the energy needed to transfer that around the home, in red. And so what you can see here is that we've got 3 points here versus for each of those specifications at different outdoor air temperatures. And so as it gets colder and colder outside, the system becomes a little less efficient and can't move quite as much heat, just because it's harder to extract heat out of that 10 or 0 degree air temperature. Historically, this equipment, heat pump equipment, has only been rated at this 47 degree test point that you see on the very right side of your screen. The NEEP has been doing some work to create a cold climate specification, and we can provide the link to that database. But they've been really working to create these test points at 17 and 5 degrees to get us some more data for how these systems will actually perform in the field. So if you're interested in finding out equipment that's really designed with this cold climate application in mind, this is a really good resource. They have a database of the equipment that meets their specifications, as well as the rated data at these additional test points. And we're actually seeing that these test points being picked up by some of the AHRI and some of the rating methods, so that we see more and more equipment being rated at these cold conditions that are really important if you want to design or estimate how the performance is going to be in a cold climate. So with that being said, we use the information provided from those specifications to do some of our sizing information. So this is a very similar curve to that last one I just showed you. This is again from specified data or laboratory measured data that is available from the manufacturer. We have 3 different pieces of equipment. So this is the same model of heat pump, but in 3 different sizes. So we have a 2-ton size in red, a 3-ton size in orange, and a 4-ton size in purple. And this is really looking at the delivered capacity on the y-axis at various outdoor air temperatures on the x-axis. And the black line on top in this chart is what we expect the heating load to be for one house. And so this is taken from kind of the design conditions from running a manual J calculation, or from looking at your utility bills. You can find out how much energy is actually needed to keep a specific house warm in the winter. And this should be done as part of any sizing design before installing an HVAC system. And so what we see in that is that at negative 11 degrees outside, which is the design condition for the metro area, it takes about 30,000 BTUs to keep the house warm. And we can assume that somewhere around 60, you don't need any energy to keep your house warm. Somewhere between 60 and 70 degrees, people typically turn off their heating systems. And so what we look at here is if we plot the capacity of each given heat pump against this heating curve, we can see the outdoor air temperature at which the heat pump can no longer meet the load of the system. For this specific house and this specific piece of equipment, we went for the 3-ton system that met the load down to about 10 degrees. This let us meet about 80% of the heat in a given heating season with the heat pump, but still maintain a reasonable startup cost. So it's sort of a trade-off you have to weigh. If you put too small of a system in, you meet less of the load, but if you put too big of a heating system in, a heat pump system in, you meet more of the load, but it gets more expensive. Typically, the typical rule of thumb that we found from these installations and looking at others' specifications and house sizes is that you're going to end up putting in about a 1-ton larger heat pump if you design for heating than if you were to design the system for cooling, like the same home with the same piece of equipment. So you're looking at about a 1-ton bigger piece of equipment, which is a pretty small incremental cost. In terms of operation, A couple of different, you're going to have different, slightly different operations for the different types of equipment, for the ducted systems or the ductless systems. So as we mentioned in that sizing chart, the ducted systems, we targeted about a 10-degree switchover. And that's the point where the heat pump can no longer meet the load at the house. So below that temperature, the backup system is going to take over. With the ductless systems, it's slightly different. Those systems will just operate no matter the temperature outside and will contribute some percentage of the heating load all the way down to -13. And so you don't really have to set a switchover point for these systems. They'll just operate as much as they can and meet as much of the load as they can. That kind of feeds into the controls and integration with the backup systems. For the ducted systems, it's really automated with that flex fuel type system with the furnace as the backup. And so the system will know when that, measure the outdoor air temperature, and will know when that set point occurs and know to switch to the backup. It also has some integrated controls that will say if the heat pump, if it's warmer than the temperature, the switchover temperature, but the heat pump still can't keep up for some reason, it also has the backup there to take over and help meet demand if the system can't keep up. The ductless systems are a little less automated because they're sort of standalone systems and they're separate from the backup, which is often electric resistance heat in a home. And so you really integrate those systems through just setting the set points slightly differently for your thermostats. So if you think about it, if you want the heat pump to come on first, you just set your indoor conditioned temperature on the thermostat slightly higher. So you set your thermostat to 70 degrees, and you set your electric resistance heat to something like 68 degrees. And so as the heat falls in the home, and it's getting cooler and cooler, and it hits 70 degrees, the heat pump system knows to trigger and starts to heat up the home, and we don't hit that 68 degrees, so the electric resistance never kicks on. And so the heat pump will be the primary system. As you move beyond the capacity of the heat pump, the temperature will drop below that 70-degree point if it can't keep up, and then once it drops down to 68, the electric resistance thermostat will see that temperature difference and kick on to become a supplemental heating system. So it's a slightly different method of operation, but achieves much the same effect, where the heat pump is the primary means of heating, and you have a backup heat source available when there isn't enough capacity. So I started to talk about this a little bit, but the furnace integration in particular is a new area for manufacturers. So with a traditional heat pump system, but before we had the cold climate heat pump systems, there were heat pumps that were available. They just couldn't really heat beyond about 30 degrees outside. And so in our climate, it wasn't really considered a heating option because so much of the heating season is below 30 degrees. And those older systems could really be installed with any existing furnace out there because they didn't have a lot of integrated controls. It was really just, is the heat pump on or not? With these newer systems that have a wider range of modulation, can heat at cooler temperatures, and have a lot more integration on the control side, it's really important to have a backup furnace system that talks with and has the capabilities needed for the heat pump system. And so right now the path to achieve that for manufacturers is to install a new furnace at the same time as the heat pump system. And you can imagine that that has a significant impact on the total installed cost. So we sort of looked at a few different options for installing this system. The first option was just to go for it, install the best furnace they had, brand new, with the new heat pump. And that really gives you the best of all worlds in terms of performance. You get that brand new air handler that works really well. You get the totally integrated controls, all the options you can do, the multi-stage fan, all those things. And it also gives you a condensing furnace. When the furnace does have to run, you have the 90% furnace. Another option that we considered was to get the really nice fan, multi-stage fan and controls, but to limit to install a cheaper furnace. So to go with an 80% furnace that's still new, so it still has some cost, but is a little bit cheaper. And we thought that might be okay because we're really trying to limit the amount of runtime on the furnace anyways. So if it's only covering 10-20% of the heating load, maybe the impact from going with the 80% furnace is worth it. So that was one option we considered. Another thing that's we're starting to see some movement in the market is some different solutions for actually doing sort of a staged installation. So if you install the heat pump, you can just install the heat pump. You match it with your existing furnace or backup system, and then when the furnace lifetime expires or dies, you replace that with the newer furnace that has all the features. And so you have sort of somewhat non-optimal performance for the first period while you're working with your existing furnace, and then when you replace that furnace, you sort of unlock the full potential of the heat pump. Another option that we get into in the full report, and I'll only briefly mention here today, just for time reasons, is the use of eliminating the furnace and going with just a plenum heater as backup. So as these heat pumps work at colder and colder temperatures, maybe there's less period of time where you're relying on backup at all, and you can get away with just sort of a boost performance. So the heat pump would still run always, and that the plenum heater could just kind of give you those extra BTUs or extra degrees of temperature that you need, as opposed to having a full furnace backup. So that's a potentially option, especially in small, tight houses that don't have as big of a heating load. So really for this project, the two that we considered were their first two bullet points, just for simplicity and to really get the best performance out of the systems. But in the future, look for those other options. In terms of the ductless system, so here's just some pictures of those components that I mentioned. The outdoor unit looks a lot like the others, only smaller because it's only a 1-ton system. You have that indoor system, indoor head system that actually distributes the heat to the house, and the thermostat. So one thing to consider when you're installing a ductless is, how do we get the most out of this system? And so this is just a simple floor plan from one of the houses with the 5 electric resistance baseboards in that home highlighted. And so when you're looking at where you want to install this unit, you can do one of several things. If you installed it in that back bedroom at the top of the screen to replace that resistance heater, you'd get a really comfortable bedroom out of that heat pump, but it would have pretty limited effect in the rest of the house because that room is so closed off. However, if you installed it in the dining room on sort of the right side of this slide, you'd have the ability to provide heat to sort of the living room, the dining room, the kitchen, maybe the den, maybe into that bathroom, and could really get more bang for your buck out of that heat pump. And so if you think about a typical floor plan, sort of the more open your house is and the more open the area is that you're installing the system, the wider heating load you can reach. Another option is to install multiple units in one home, but we really focus on just installing a single unit to see how it worked for this system. There's obviously more cost and more load available as you go to more and more systems. So just some things to think about in terms of different scenarios that you might use a cold climate heat pump. If the house has a sort of full forced air heating system, it's probably easiest to go with a ducted system. This is sort of a like-for-like replacement to either your furnace or air conditioner. And again, if you do have air conditioning, you have that extra savings potential from the more energy efficient air conditioning as kind of a bonus. And so that's really the type of system you're looking for. One thing to consider here is if either the furnace or the air conditioner needs a replacement in that home, it really helps the cost effectiveness of these systems to look at upgrading or the incremental cost of comparing to a new furnace or a new air conditioner as to going over to the heat pump. So just a thought there. The ductless mini split really becomes attractive in houses that have hydronic heat or electric resistance heat, where you don't have that central ducting system to rely on to transfer the heat. And so you can use this much more efficient heating source in sort of the main area that needs heating in the home, and have this added benefit of cooling that might be harder to get to those areas in the house if you have hydronic or electric resistance. And so that was really the scenario the electric resistance scenario is really the one that we saw in this project. I will note that most of the installs for these ductless systems that happen in areas where natural gas is available is as sort of a supplemental heat or cooling to an area that they can't reach in a hydronic house. So if you put on a new addition and there's no central ductwork, you could stick one of these ductless systems in and it would be a pretty unique solution. Or if you have hydronic heating and you have a bedroom that's always really hot and you want to get some cooling in there, you might be able to put a ductless in that has some benefits on the heating side as well. So just something to consider in terms of install. So let's start to get into some of the performance of of how these systems actually ran once we installed them. And so when we're in heating mode, there's kind of three main modes of operation to think about. Two are really straightforward. First is just when the air source heat pump is running. So this is any time you're above that sort of 10-degree switchover point in the home, or above the -13 if you're ductless. The heat pump's just going to run whenever there's a demand for heat, and it's going to get its COP and capacity for that sort of outdoor air temperature. If you're below that set point, if it's below that 10 degrees out and the heat pump can't keep up with the load in the house, we're going to use the backup heating system, or the LP furnace. And that's pretty straightforward. It's going to run much like a standard furnace. The one that's different is the defrost mode. So if you're running this air source heat pump for heating in the middle of the winter, you're going to get times when that coil gets cold outside. And so the system wants to protect against a buildup of moisture and condensate on that coil. And so it does that by essentially running the furnace at the same time that it runs the heat pump in reverse, basically. So you're going to run the refrigerant in reverse so that it takes heat from the furnace and circulates it through the outdoor coil to warm up the coil and limit potential for frost buildup. The way this is done is purely on a temperature measurement outside. So whenever the conditions are present near the coil for there to be frost buildup, essentially anytime it's below 35 degrees right by that coil, the system will run in reverse, heat up the coil, and then restart kind of the countdown until the temperature drops in there again and the defrost has to run. This is a pretty conservative method of operation, so we don't see any frost buildup when the system runs like this. We do some work, and we get into it in more detail in the report at looking at various ways that this conservative operation might be changed to sort of run only when defrost is actually needed, not just running anytime conditions are present. But that's sort of a future improvement type constraint, and as I said, we get into that in the report. I'm not going to focus on it too much here. So here's some installed performance for various heating cycles in one of the sites. And so each of those modes is a different color on this chart. The kind of orangish color is the heat pump only mode. The purple color is the furnace only mode. And the kind of blue color in between is all those times that defrost kicks on during a cycle. And so we're looking at the coefficient of performance, or again, essentially the efficiency of the cycle, versus the various outdoor air temperatures. And so you can, if you look at the very cold temperature performance down there when it's 0 degrees outside, essentially any time below 10 degrees, you see a lot of those purple events somewhere around 80% efficient. And that's the furnace only running in backup, each cycle running on at its rate, about its efficiency, and those are pretty consistent. When you get above 10, you see the heat pump events in orange that sort of range from about 1.75 all the way up to almost 4 in terms of COP, and that really lines up with the manufacturer specification. So that heat pump is definitely doing what it does. It's running at very efficient, it's providing at least twice as much, if not 3 times as much heat to the home as it takes to move that heat from outside to inside. The stuff in the blue is, you see a lot of noise there, and that's because that's a heating cycle where the defrost is kicked on. Sometimes when it's essentially only defrost running, you see there's almost 0% efficiency, and that's because the system is moving almost all of the heat from the furnace to the heat pump to keep it from frosting up. At other times, it's much more efficient because the heat pump has been on for a long time, and then the last couple of minutes of an event turns on the defrost and makes it slightly less efficient than the heat pump mode. So that's why you see such a wide range of performance there. But you can see that when you're in defrost mode, you are seeing a significant reduction in efficiency than when the heat pump is on. And so it is important to understand how that defrost is running when you want to estimate what your savings are going to be. So one other thing to point out here is that these numbers are all sort of installed performance. They're not sort of the lab-rated efficiency that you see with equipment. So equipment, when it's measured and specified, your AFUE, your efficiency, your COP that you see written on the manufacturer's decals really represents steady-state operation at a given set of operating conditions, which we rarely see when we're out in the field. We see a lot more transients. We see things ramping up and cooling down. we see operating at a lot of different points. So that's one thing to keep in mind here. You know, I said the efficiency was around 80% for the furnace when it's a 90% rated furnace, and that's because it takes a while for the furnace to ramp up to its steady state efficiency. And all this plot shows is just sort of that instantaneous efficiency of the equipment, or the kind of cumulative efficiency of a cycle, and how it takes kind of 10 to 20 to 30 minutes to get up to that condensing level of efficiency. And so that's important to remember when you look at some of these numbers, is that these are really the field rated conditions. And that sort of jumps us into this next plot, and I apologize, there's a lot of data here in one slide, but I just wanted to give you kind of an overview of the operation of all these different sites. So this has all 6 sites on top of each other here, both ducted and ductless sites. And so if you look at it, you can see kind of 3 regimes where we've got kind of the heating performance on the left-hand side of this slide from kind of negative 20 all the way up to 50 degrees outside. We see positive COPs ranging from about 0.8 all the way up to 5 in some instances. And then as we move over to where it gets hotter and hotter out, we see that efficiency go to 0 and then to negative where the cooling comes on. So in these calculations, we're counting energy removed from the house as cooling as a negative COP. And so that's why you can really see these systems are providing cooling. I don't want to get into that analysis too much. There's a whole bunch of different things there, but they are providing really efficient cooling as well out there where it's like 75 degrees out. So I just wanted to show that. But if we zoom in here on the kind of heating performance, and you can kind of somewhat ignore the data points around 0 on the right-hand corner. That's essentially times when it's warm enough out that the heat pump is basically barely on, or it's partly in cooling and partly in heating, and so you get some numbers that are near 0. But if we look at the heating performance down below 0, you can see that for the ducted systems, those daily system efficiencies are a little bit below 1, where we're running both the backup furnace as well as the heat pump, as we get a little bit warmer out. But the ducted systems, the kind of blue and pink, have efficiencies that are greater than 1, and that's because that heat pump is still running all the way until negative 13 degrees. And so we're still seeing COPs that are higher than 1, which is pretty great. We had some really cold temperature performance of those ductless systems. This is a similar data. It's just grouped kind of together to give you a more clear picture. So these are the 4 ducted sites. This is just the heat pump, so we've sort of eliminated the backup performance in these slides. And the bins here are kind of the box plots that show the interquartile range, or essentially you can think of the color representing over half of the runtime of the piece of equipment. And so you can see when it's between kind of 0 and 10 degrees outside, we have COPs that are kind of between 1 and 2 depending on the piece of equipment, and they kind of get higher and higher as we move along. And so once you're out at 40 or 50 degrees, you can see kind of the average COP is up towards 3, with the caveat that one system at site 4 really gets efficient out there. And that has a lot to do with kind of the airflow that's achievable and some of the operating conditions at that site in particular that really let it be extra efficient. But the big takeaway here is that kind of from that point where the heating kicks on in full at around 50 all the way down to that changeover point at 5 or 10 degrees outside, when the heat pump is running on its own, it really matches up with those specifications supplied from the manufacturer. And this is really encouraging. These are some really high COP numbers, which really indicate the potential for savings. And so it's really, everything's really straightforward when the heat pump is on. Things match the conditions. They work great. As I mentioned, though, there's this propane runtime that we need to account for. And that really comes in through two ways. The operation of the equipment at temperatures below that switchover point, as well as the defrost. And so I just wanted to kind of walk through one day of operation here to sort of give you an idea of how that works. And so I apologize for kind of maybe the confusing nature of this slide. I'll walk you through it, but I just wanted to kind of highlight a day in the life of a heat pump. This is one site on a day when it's about 17 degrees outside on average, so we're kind of fluctuating around that 10-degree set point. So this is just a time series plot from midnight one day to midnight the next day for 3 different variables. The top variable is the outdoor unit in green. So that's essentially the heat pump energy use. So that's in watts. It kind of goes from 0 at the bottom where it's off up to its max rate of about 3,500 watts. So you can see that it's either off or sort of operating somewhere in the middle with a couple of spikes up to almost its full capacity. The line in the middle is the fuel consumption or the furnace running in BTU per hour, which goes from 0 to its max fire range of about 80,000 BTU per hour. And then the final chart is the outdoor air temperature. With that red line on that chart represents that switchover point. So you can see for most of the day it's around 20 degrees outside, so it's warmer than its switchover point. And then just before midnight it switches into a time period where it's below 10 degrees out, right around or below 10 degrees out. And so it's below that set point where the heat pump can't keep up. And so if we look at a couple of different points in this day, in the evening here, we have a time period where we get a nice long, the heat pump's on for several hours in a row, where it's about 15 degrees outside. The heat pump's providing more output than is necessary to keep the house warm. So it's meeting capacity at that 15 degree set point with no backup, no help from the backup system. And it's doing a good job of meeting capacity. And it's actually only running at about 80% of its capacity there. So it could actually provide enough heat to keep the house warm at an even colder temperature than that, which is really encouraging. The other thing that jumps out that we notice is that there's all these time periods where the propane is coming on, but it is warm enough outside that the heat pump can meet the load. And that's all those defrost cycles in this house, where the temperature sensor in the outdoor coil is registering a temperature cold enough that defrost might be present. And that amounts to 10% of the day in this case. And if you remember back to that mode efficiency slide, you're seeing efficiencies in those time periods that are anywhere from 1%, the heat pump operation, all the way down to 0% effective while it's running because it's in defrost. And so that's a potential for a pretty big impact on the system. The other thing we notice is that out here where it's after we've dropped below the set point of 10 degrees, you can see that the heat pump is turned off and that the furnace comes on and runs kind of the whole time we're in that mode. And on this day, that's about 8% of the runtime. But so it's an important factor to know over the course of the year, sort of how much you're doing this LP heating because it's below the temperature and how much you're doing because it's in defrost. When we move to the results, the thing to keep in mind is that kind of on average, about 50% of the LP used in this house goes to that defrost mode, and about 50% goes to the heating mode, or the below set point mode. And that below set point mode is only about 10% of the total usage in the year. So we're looking at a kind of a 10 to 15% penalty just from defrost. Another thing on the cold temperature performance, this is a plot, again, looking at those box plots to kind of give you an idea of where the median and most of the runtime is against various outdoor air temperatures. And the thing to really look at here is that as you move to colder and colder temperatures, as you go to the right on this chart, the system holds capacity pretty well. So the average capacity goes from about 20,000 at 30 to 35 degrees outside, and only drops to about 19,000 BTU per hour between 5 and 10 degrees outside. So we're not losing a lot of capacity, and a lot of this ramping you're seeing is not even at full capacity of the system. It's really just the needs of this house. So the important takeaway here is that these systems are matching their specifications in terms of how much heat they can actually deliver, and that they hold pretty well over the range of temperatures we see in these houses. So there's a lot of information on this slide to make that point, but that's the key takeaway, is that the systems are really doing the job they claim they can do at 5 to 10 degrees outside. And this is for a ducted system. I can say the same thing for the ductless. I just don't have a plot on this chart, in that it really does hold its temperatures and its specifications down to those rated conditions. We do have one of the homes that we installed was that it actually happened to be in Wisconsin. It was in Superior, but they had installed the heat pump, the ductless heat pump, just before the start of this project, and so we were able to add our instrumentation and get some really good information out of it. But that homeowner has now had their ductless system in for 2 full heating systems, and they've used it so little that they have started to remove some of their resistance baseboard heat in Superior, Wisconsin, so northern Minnesota up by Duluth. That's a pretty encouraging sign. That homeowner, I will say, he does have a fireplace, so he can get some supplemental heat in other ways if he has to, but he really doesn't use the backup heat at all in that home and just relies on the ductless system. We have some evidence that on a couple of hours when it got really cold in Superior up to like -20 or so, that heat pump actually still ran out way below its rated conditions. It's not nearly as efficient as it can be when it's really cold out, but it's nice to know that it will actually provide some heat at very cold conditions. So just a little comparison between the 2 system types. Like I mentioned before, the rated capacities and the sizes of the ducted systems are much larger. So that lets you heat the whole house. It gives you larger airflows, lets you cover a bigger fraction of the load, but they do kind of become restricted at slightly warmer temperatures, whereas the ductless systems are really targeted to meet the design load of a specific area or a whole house if it's a small open floor plan like an apartment or something. They're really good applications there, and they also go to lower temperatures, that -13 degrees outside, just to keep in mind. So I want to get to energy use summaries sort of as we go through. So we did these really detailed models of the systems that I've showed you some results for, and we also got some really good data characterizing the heating load of the house. And so so we kind of use those 2 models and typical temperatures to kind of come up with our average performance for a given year. So this is just a plot of kind of how the system works. And so in this plot, the colored points are when you're in the heat pump mode. When the heat pump's running, you have propane consumption in purple and energy consumption from the heat pump in orange. And this is compared to the black line, which is if you just heated the house with the furnace. So as you get down to those really cold temperatures of -10 or so, you can see that the heat pump is basically turned off and it's all relying on its purple backup system in propane, and it much matches what the house would be like if it was just being kept warm by a furnace. And then as you move to warmer and warmer temperatures, you can see that heat pump takes over more and more of the load. One thing to remember when you look at this slide is that this is the energy used by the house. So the heat pump has an efficiency or a COP of about 3 as compared to the furnace that is less than 1. So any BTU consumed in electricity in orange is essentially 3 times more effective at heating the house. And that's why in times when the heat pump is dominating, like when it's 20 degrees outside, it doesn't actually look like it's using that many more BTUs than the furnace is. So just in kind of summary of the energy use of the houses, so here's each of the houses, and this is looking at the energy consumption in therms per year. On this chart, the blue is propane usage, and the red is electric usage. To the left-hand side of each site, you see kind of the baseline, assuming we were just using a furnace, and the right-hand side is the cold climate air source heat pump. On the sites 6 and 8, the 2 ductless systems, you can see the baseline is just all electric resistance heat. So this really gives you an idea of the savings potential in terms of site BTUs. We have really large savings percentages here, but you can see we've drastically reduced the propane usage while increasing the electric usage because the heat pump is using more than just the fan in the furnace case. I will point out here is that, again, there is cooling savings with these systems as well. We're looking at, on the ducted side, typically you're increasing the SEER in cooling from about 13 in the baseline case to something like 16.5 up to 20, depending on the heat pump model that's selected, which is a 300 to 500 kWh per year, or about $50, somewhere in that neighborhood, savings just from the cooling side for these homes, kind of on average across the state. obviously smaller if you're northern Minnesota where there's no cooling, and more if you're in the metro or southern Minnesota where there's more cooling. So here's the kind of big picture savings for each site, for all 6 sites, both the ducted and the ductless. The first 2 columns are just sort of to give you an idea of the magnitude of the heating load. So you can see the ducted systems are kind of between 20 and 40,000 design conditions, which is kind of the typical range we expect to see in Minnesota houses. None of these are giant, 5,000 square foot houses. None of them are tiny 600 square foot houses. They're all kind of a typical, 1,500 to 2,000, 2,500 square foot home with sort of a regular level of insulation and those sorts of things. You can see that the ductless numbers, those are sort of estimated because they don't meet the whole load of the house, but they're much smaller, so they're meeting a smaller amount. So you can see we have some savings numbers both in terms of BTUs used on site, the site energy reduction between kind of 37 and 55%. The cost reduction to the homeowner, that's the annual heating costs reduction from 30 to 50%. And then the other category we looked at here is propane reduction. So you can see over 50% reduced propane usage at all of the ductless sites. And then we also have kind of the dollars per year saved at each home. And so you can see it's a big range. The heating loads differ. The amount of propane usage differed at these houses, things like that. So we have a pretty big range of savings, but around $500 a year on average. In terms of install costs, so this is this is a lot more theoretical number. We only had the 4 ducted systems, so it's probably not a great average number to use. We paid about $14,000 to install these systems. That included that new furnace, and in 3 of the 4, it was a new condensing furnace. So that was about half of the cost, maybe 40% of the cost in most of these cases. We also paid some money for the instrumentation and things, so there's some small addition, maybe $500 for that. The biggest thing I think here is that most of the contractors we worked with weren't very familiar with these cold climate systems. They had had some experience with non-cold climate heat pumps and lots of experience with AC systems. And so there's probably some kind of safety / risk factor built into these numbers that cause it to cost a lot more. If you look at the second bullet point, this NREL maintains sort of a national database for installed costs, and we've got some numbers here that we're showing for just the heat pump for a new condensing furnace and an 80% furnace, and then kind of the comparable AC cost for a new high SEER AC system. And those are sort of probably better numbers to use in terms of kind of an average or what you might expect to pay in a program. And the thing to really jump out here is that the time where this starts to become really attractive from a payback period, where you get paybacks around or under 6 years, is when you're looking at already replacing either your furnace or your AC system. You can get that incremental cost down. If you have to replace both, the incremental cost is basically nothing. It's maybe a few $100s. But if you only have to replace one or the other, you can get that incremental cost in the $3,000 area, and then you're looking at much better paybacks. So that's something to keep in mind in terms of how you might stage this. For the ductless systems, it's really hard, and I haven't here in the presentation tried to present any numbers for paybacks. We can get into that. I get into that some in the report, but there's a ton of variance here in kind of what fraction of load you can cover and what the actual cost will be, depending on sort of how susceptible your house is to interrupting the aesthetics, because you're putting this system into the conditioned space as opposed to into a mechanical room. And so there's a lot more variables. These are just some summaries of the numbers. I've mostly went over these already. The couple of new points to point out is that the ducted systems on average met 84% of the heating load in the houses. So we're only using the backup systems for about 15% of the load. That includes the defrost runtime. The propane reduction, we had on average 64% reduction. And the great thing is that for all of these houses and what we think is most of the houses in the state, that would reduce the propane consumption below 500 gallons, which is the typical storage size at a residential house. And so what that means is you can avoid filling up your propane tank in the winter when it's much more expensive to do. So that's pretty encouraging. And so another thing to note is that we had kind of installed system COPs, so total air source heat pump plus backup, of around 1.3 or 1.5 for all of these houses, which is, you know, a significant improvement over the kind of 1% you're getting with electric resistance, or 0.8, 0.9% with a furnace. I'm not going to get, as we're starting to run out of time, I'm not going to get too deep into the policy part of this. I've talked a lot about switching from propane to electric, and there's a lot of sort of implications from a policy side with fuel switching. We had ACEEE as a partner on this project, and they did a report into sort of some of the precedents and history and potential next steps in this arena, and there's a really great report on our website about that work. There are some precedents in state and around the country that lead to including this on terms of a sort of a net BTU analysis, and there's some really good information there. So I'll encourage people to look at that. And in conclusion, the heat pumps really, when the heat pump was on, worked great as we would expect. Really good performance. The big variability in all of this is kind of how much freeze protection and how well you integrate it with the backup. Those can be done very well if you kind of follow the guidelines we sort of put forward here. The systems do work at cold temperatures, and if you stage the install right, the systems can be really attractive. We kind of touched on most of these things. Upfront costs are a little high at this point if you're not looking at sort of this incremental or staged replacement. So looking at ways as the system advances to get those costs lower, as well as improving the performance through limiting defrost and getting that operation point lower and lower. I do want to kind of plug, stay tuned to CE for kind of future work. We're doing some work to sort of start looking at the different metrics that might be used to evaluate heat pumps. So I kind of talked about site energy and kind of efficiency and cost, but also important, and we touch on some carbon reductions that are a potential here, source energy, kind of those sorts of things, and how they might change going forward with the equipment improving and changes to the grid. So that's some upcoming work that CE is just kind of launching now to stay tuned to if you're interested in those areas. With that, we got a couple of audience polls that we'd like to get to.
Hello, everyone. This has been quite an overwhelming, I'll say overwhelming in a good way, amount of information, and there are lots of questions that have been coming through. We were going to do 2 poll questions because there's a lot of people from the industry on. We have about 84 people that have been with us today from 14 different states. But I think that we actually have a follow-up question or 2 in the poll that will pop up once you sign out of the webinar. So I think we're going to forego that just so we can get to a few of your questions. And because there are so many, we're going to stay on for an extra 10 or 15 minutes to get through some of those questions in real time. And then beyond that, any that we don't get through, we will take per usual and answer them in writing and post them on our website, as well as send them out to all those that have registered and are tuned in right now. And so I just wanted to also mention where on our website you can find more information about air source heat pumps. The URL at the top of this page is where you can go. It's sort of a shorthand for the project page of the work that Ben has just been discussing. And also, if you were to move over to the resources tab on our website, there's a drop-down menu there for webinars and events, and that is where we archive all of our webinars, and you'll be able to find the archive of this probably in the next day or 2. With that, I'm going to turn it over to Mark Garofano at the Department of Commerce to lead us through some question and answer.
Thank you, Megan, and really interested in all these questions that have come in and want to hear what Ben has to say in response. First question is, does the technical reference manual currently address the heating side of air source heat pumps at all? Ben, I can probably answer this one since I manage the technical reference manual. And yes, we currently have this measure in the technical reference manual, but it deals with more of the typical air source heat pumps that aren't the cold climate ones. So this study is going to be building on that calculation. The next question is, if you upsize the air source heat pump system, how will that affect the summer operation, particularly with respect to dehumidification control? Will a dehumidification performance suffer because of the increased size?
Unmuted.
Sorry, I just had an issue with the muting there. But there's actually been quite a bit of work on this issue in general for AC oversizing. One of the nice things with these heat pump systems is that the modulation is pretty significant. So you have a wide range of difference. So on the bigger units, when you're increasing the max capacity, you don't have as big of an impact on the minimum capacity, and so you're still able to ramp the systems quite a bit. And so you can still have long run times in cooling. We did do a little bit of analysis looking at that. It wasn't, as I said, it wasn't the primary focus of this report, and we sort of relied on that, some work from others, but it doesn't look like it will have a very significant impact on the cooling side from just a 1 ton increase. If you were to increase more and more to try to chase that last couple of % of heating, then you might start seeing a significant impact.
Okay, thanks, Ben. The next question is, are the issues solutions for integrating heat pumps with furnaces the same or different for integrating with boilers?
They're different. So the integration with the furnace really comes down to the fact that the furnace and the heat pump use the same fan to distribute the air through the ductwork. And so if you're relying on an existing furnace fan to work with the heat pump, you're sort of limiting the amount of control and stages of fan operation. So you're probably only going to have 1 or 2 speeds of fan operation on an existing furnace, where the kind of new air handling units have either lots of stages or infinite modulation. So that's really the key when you're integrating with an existing furnace. With a boiler system, you probably don't have a fan because you're using hydronic distribution. So then you're looking at installing a new fan either through a ducted or more likely through the mini-split system that has its own fan. And so the integration issues aren't there. Then it's just about integrating the thermostats so that you call for the heat in the way that you want to, as I mentioned, by sort of offsetting them by a couple of degrees one way or the other.
Okay. Our next question is, did you study the effects on sizing of heat pumps from new inverter-driven air source heat pumps?
Yeah, so I guess I didn't get into the technology specifically, but as far as I'm aware, all of these cold climate systems rely on the inverter-driven technology. That really what that means is it just lets you have this variable capacity of the heat pump system. And so that's really what types of systems we're focused on here, and that's really what unlocks that cold climate potential of these systems. So that's really was the focus of this work.
Okay, then the next one, looking at the data on slide 26, showing the heating efficiency versus temperature, how long is the time interval connected with each data point? Is it a day, an hour, or some other unit?
Let's see. 26. Okay, so this slide is really looking at the event-based, so it can be as short as a couple of minutes if the system is really only on for if the system only takes 5 minutes to meet the set point of the thermostat, then that's represented as 1 point. If the system is really ramping with the thermostat and it's on for 3 hours straight, that's also only going to show up as 1 point on this slide. This is really an event-based analysis. Whereas if we're looking at these slides, these are the daily averages. So these are kind of summing up all the data from the furnace and the heat pump for a given day. So that's why you see a lot more noise in these charts, because there's a lot more variance as to how the system is operating over the given day.
Okay. Next, you said the crossover points in your study are 10 degrees Fahrenheit for ducted systems and negative 13 degrees Fahrenheit for ductless. Do you know what crossover points contractors are designing in practice?
Yeah, so that's a big issue, and that's part of what I got into when I was talking about some of the install costs. Traditional systems that are not cold climate systems that don't have this ability to heat at really cold temperatures, those are being installed with a changeover point up by 30 degrees. There's no real difference in the actual install between those systems and these new ductless systems. It's just that their capacities are much greater. So we're really sort of at the forefront of how we design these systems to meet that point. And so we decided, based on some background analysis and some other work done in some more moderate climates, that we thought that we could do 10 degrees. And we actually changed it to 5 over the course of the project. So we think that we can do, so you can do sort of some of those colder degree temperatures. But in practice, there's not a lot of people doing this yet with these cold climate air source heat pumps. So that might be part of the outreach we need to do as part of this project, and is certainly would be part of the outreach you would want to do as any kind of program, would be how to actually get these systems installed right. With the ductless systems, they're pretty much standalone, so kind of whatever the system is capable of, it will do, and then default to backup when it can't keep up. So those have sort of been changing as that technology advances. They were -5 a few years ago, and like I mentioned, there's some new equipment that's out now that's -20. So those are nice because they're just kind of standalone, and you just install them, and they kind of cover the range that they can.
Next question is, what is the user feedback on air source heat pumps, the ductless, and the locality of the heating cooling, as well as acceptance of how they look installed on their wall?
It's a good question, and I kind of mentioned it briefly with the sort of part of the install cost is actually getting it in the house and figuring out how to get it installed in a way that's aesthetically pleasing. So like I mentioned, we only had 2 ductless sites. One of our houses had made this decision to go to ductless before the project, and we just sort of jumped in there. The other one had all electric resistance, and we recruited to do the mini split. Both our sites, I really like them. They thought they heated very well in the areas that they were targeting. They did have a good integration with their electric resistance and only a small separation between when they came on, and so the heating was really uniform. It's obviously a small sample size of only 2 houses, but I guess in general they do seem like they have a pretty good and growing market share. So the reviews aren't too negative. Obviously, they provide pretty consistent heat, and they have really long run times. So they have sort of the performance that we tend to see with systems that people like and feel comfortable with. Aesthetics, I guess, just kind of comes down to what people can handle or what they like. They are pretty attractive units. They've come a long ways in the kind of 5 years that I've seen them in existence. They're pretty well contained, and they don't sort of have any weird parts or anything like that. They look well designed, and they're not that big. They're a couple of feet long by maybe a foot tall, so they don't, they can go kind of in lots of different places. So in general, people seem to be pretty happy with them.
Okay, thanks for your answers, Ben. We still have about 10 questions on the list, and we've gone 10 minutes over already. So I think we're going to cut off the webinar at this point and be posting those answers on your website for any questions that were not answered during the webinar here.
Great. Thanks a lot, Ben. That was a really great presentation and a lot of really good information and a lot of good things to think about and follow up on in the future. So in addition to on CEE's website, the recording of this webinar as well as the final report will be available on the Department's Applied Research and Development, or R&D, webpage, which is shown here. And when available, you can link to them from either the webinar quick link or the card search link, which is indicated on this slide. This R&D page has additional resources and information related to the CARD program and to CARD research projects, which you may want to check out. The web address is at the bottom of this slide. So thanks again for participating today. We appreciate your interest in the results of CARD projects. Before we leave, I just want to take an opportunity to mention actually four upcoming webinars that are CARD related. One is on November 14th. The Center for Energy and Environment again will be presenting results from their project which developed quality installation and quality maintenance guides for energy efficient operation and recommissioning of pools in Minnesota. On the 29th of November, Seventh Wave will give a webinar on their investigation of strategies to enhance new construction programs through performance-based design and procurement. On December 7th, Michael's Energy will be discussing their project which tested two ongoing commissioning approaches to improve the efficiency of outpatient medical clinics in Minnesota. And on the 14th, the Center for Energy will be back again to conduct a webinar on their field study to determine the increased efficiency resulting from the installation of an innovative moisture and heat transfer retrofit device on residential furnaces. Announcements about upcoming webinars and other news related to the Minnesota Utility Conservation Improvement Program can be found in our SIP newsletter. To sign up for this newsletter or to receive e-news on a range of other energy topics, use the link on this slide to go to the email sign-up page on the department's website. In the meantime, please feel free to contact me if you want more information on how to sign up for these webinars or if you have questions or feedback on the CARD program. You can also let me know of any suggestions for improving these CARD webinars to make them more relevant to you. Thanks again and have a great day.